Welcome. Pay close attention to what just happened, because we are witnessing one of those moments that divide the history of engineering into a before and after. SpaceX has formalized the acquisition of xAI. We're talking about a transaction valued in the context of $1.25 trillion. Yes, with a T, involving a direct disbursement of $250 billion to integrate something that seems straight out of a science fiction novel, but which is pure physical necessity, uniting the most powerful rocket in history, Starship, with the most voracious computing demand we've ever known, artificial intelligence language models. You're on the channel The Next Framework in Engineering. Our goal is clear: to understand the deep foundations of current engineering so that you can build the future using artificial intelligence. Today, we're going to analyze the strategic integration of orbital computing infrastructure. Why the hell do we want to put servers in space? Is it madness, or is it the only out? If SpaceX is making this move to launch data centers into space, it's because they've already done their feasibility study, and today on this channel, we're going to attempt to replicate it. What we're witnessing is a very audacious technical thesis: the displacement of AI training infrastructure from the Earth's surface to low Earth orbit, or LEO. And watch out, because although this has massive economic repercussions, where we've seen nuclear energy companies like Oklo or NuScale drop 7% in a single day, what interests us here is the engineering. The market is rotating capital from terrestrial nuclear energy to space solar. Why? Because physics dictates that if we solve the thermal problem, space is the definitive place for computation. To understand this maneuver, we first need to understand why Earth has become too small for us. Elon Musk and his team have identified what we call the Terrestrial Energy Wall. Currently, artificial intelligence is crashing into 3 physical limits on our planet due to the electrical grid, thermal dissipation, water, and bureaucracy. You can see this video where we've already talked about it. The merger of SpaceX and xAI proposes to bypass these limits. We move the hardware to space. There, energy is abundant and the ground is infinite. We transform a problem of energy generation into a problem of thermal management and launch. Let's break down technically how this is done, point by point. Let's talk about the energy architecture. The fundamental advantage of space is solar irradiance in the AM0 spectrum. On the Earth's surface, we live under what we call air mass 1.5. The atmosphere filters the light. We receive about 1,000 watts per square meter in the best case scenario, but if we average it daily between night and clouds, effectiveness drops to 20 or 30%. It's inefficient. However, in orbit, in AM0 conditions, air mass 0, the solar constant is 1,361 watts per square meter. It's brutal. There's no atmosphere filtering the high-energy ultraviolet photons. This allows triple-junction solar panels made of gallium indium phosphide, gallium arsenide, and germanium to operate with efficiencies above 30 or 35%. If you want to know this technology in detail, we have a complete satellite course on the channel.
Thank you very much. I'll continue. Additionally, availability is total. If we place these data centers in a heliosynchronous Dawn-Dusk orbit, the satellite rides on the line separating day from night. Result, it receives sunlight 24 hours a day, 7 days a week. This eliminates the need for massive battery banks. And this is key, engineers, because batteries are the heaviest, most expensive, and most dangerous component of any renewable system. By eliminating them, the rocket's mass equation improves drastically. Now, not everything is perfect. Here we enter the true engineering challenge, the final boss of this video game: thermodynamics in vacuum. Many people think space is cold, and yes, it is, but vacuum is above all a perfect thermal insulator. On Earth, if your computer heats up, a fan moves air and the heat goes away by convection, or we use water to carry away the heat. There's matter that steals the temperature, but in space there's no air, there's nothing. The only way to remove that heat is thermal radiation. Here, Stefan-Boltzmann's law rules. Don't be scared, the formula is conceptually simple. The dissipated power is proportional to the radiator area and to the 4th power of temperature. What does this mean? That to dissipate the heat from a high-density server rack, let's say about 100 kilowatts, we need immense radiator surfaces, much larger than the solar panels themselves. The technical solution proposed by this report requires deploying gigantic radiators made of composite materials with high emissivity, close to 0.9. We need phase-change thermal transfer fluids, known as heat pipes, that move heat from the chip to those exterior panels so they can shine in infrared and launch the heat into the universe. This is where Starship comes in. Starship's cargo volume is the only existing platform capable of launching these massive folded radiators. Without Starship, thermodynamics makes this project unfeasible. Let's move to the third critical point, electronics and radiation hardening. The space environment is hostile. We have single event effects, SEE, and total ionizing dose, TID, basically high-energy particles that pass through transistors. Modern AI chips, like those used by xAI or NVIDIA's H100s, are manufactured at 3 or 5 nanometer nodes. They're tiny and extremely sensitive. A radiation impact can change a 0 to a 1 and ruin a calculation. The traditional space industry uses Rad-Hard, radiation-hardened chips. They're old, large, slow, and extremely expensive. That doesn't work for AI. We need speed. SpaceX's strategy here is brilliant in its pragmatism. Instead of shielding the chips, they assume they're going to fail. They use commercial hardware, COTS, and apply massive redundancy. Imagine 3 processors doing exactly the same mathematical operation at the same time. A voting system compares the results. If 2 say 4 and 1 says 25, the system discards the one that failed, probably impacted by radiation, and moves forward. This allows using the fastest hardware on the market without waiting years for space-grade certifications. It's computational brute force applied to reliability. Note, this is just a first idea for mitigating these problems, but there are many more ways. Soon we'll have a video on our secondary channel, The Next Framework in Space. Subscribe if you want to see it.
Thank you very much. I'll continue. Fourth, let's talk about connectivity. What good is trading in AI in space if we can't download the data? This is where photonics comes in. Latency is the enemy of real-time inference when you chat with the AI, but for training massive models, what matters is bandwidth. The constellation will use optical intersatellite links, or OISL, basically lasers, technology already proven in Starlink V2 satellites. An interesting physical fact, light travels 30% faster in the vacuum of space than through glass fiber on Earth. The refractive index of glass slows it down. In vacuum, it flies free. The network topology will be an orbital mesh. Satellites will pass terabits of data to each other via lasers to train the model in a distributed manner without needing to touch ground. This has an additional strategic advantage. It keeps sensitive data and processing outside of any specific national jurisdiction. It's a data cloud literally above borders. And what about the data sent to Earth, also by laser? We'll leave that for a future video dedicated to it. Of course, as engineers, we must be critical. Not everything is rosy. There are critical challenges and limitations that could derail the project. The first is zero maintenance. In a data center on Earth, if a hard drive fails, a technician goes and replaces it. In space, you can't send a technician. The hardware failure rate must be orders of magnitude lower, or redundancy must be so massive that it increases the launch weight too much. The second is degradation. Solar panels in space don't last forever. UV radiation and atomic particles degrade the cell, making it lose efficiency, approximately 1 to 2% annually. The lifespan is limited. The third is Kessler syndrome, or space debris. Placing such massive critical infrastructures in orbit increases the risk of collisions. A data center worth billions of dollars destroyed by a screw from an old rocket is an irrecoverable loss. And finally, the launch cost. This entire plan, all of this engineering, depends on a single economic variable, that Starship achieves its cost per kilogram targets, below $100 per kilo. With the current costs of a Falcon 9, this proposal would be economically absurd. We need access to space to be cheap and routine. We have videos on our channel where we analyze Starship's mass production for the coming years. To conclude, I want you to take this idea home. The acquisition of xAI by SpaceX and the Orbital data center plan is not a millionaire's whim. It's a brute force engineering bet to bypass the physical limitations of our planet. Technically, we've seen that the biggest obstacle is not getting energy, the sun gives it to us for free in space, but getting rid of the heat. The thermodynamics of radiative cooling is the real bottleneck. If Starship manages to make heavy cargo transport routine, space will become the natural environment for artificial intelligence. Unlimited energy, zero regulatory latency, and natural cryogenic temperatures if you stay in the shade. This strategy is positioning SpaceX and xAI not just as leaders, but as the pioneers of a Type 1 computing civilization on the Kardashev scale. They're leaving terrestrial nuclear infrastructure as a mere transition solution. The market is already looking up, toward orbit. And this is where you come in. The future of engineering will require professionals who understand photonics, thermodynamics in vacuum, and fault-tolerant distributed systems. That's the next framework. I'd like to leave you with a question to reflect on and leave in the comments. Given the thermal and radiation challenges, do you think commercial hardware redundancy will be enough to keep these systems stable in the long term, or do you think the space environment will force the development of a new generation of hybrid chips? I'll read you in the comments. I'm your instructor on this journey toward the future of engineering. See you in the next technical analysis. Keep building.